Okay, welcome to another video guide on your Module 3. So for this video, we'll be focusing on instantaneous acceleration. This is still part of lesson 3.1, uniform motion. So you have just worked on instantaneous velocity. Now we work on instantaneous acceleration. So we actually want to describe our instantaneous acceleration the same way as we described our instantaneous velocity. So to get the instantaneous acceleration, Um, before I proceed, then let's first describe what an instantaneous quantity means. An instantaneous quantity, for this case, an instantaneous acceleration or velocity means that quantity for that specific period of time. So for, let's say, at this very moment, I'd like to know how fast I am moving, but I can't know that because time always moves forward and we cannot take a perfect snapshot in one at an exact time. So what we do to get an instantaneous quantity is to take the interval of your observation. So for the case before, since we described our average acceleration as like the change in velocity per unit time, that unit time must be extremely close to zero or must be very small for us to get an instantaneous quantity. So we want, let's recall our acceleration from page 9. We know that the acceleration is the change of your velocity with respect to the change in your time. A short interval of time means that delta t must be as small as possible, and it must approach zero. Therefore, we must take the limit of this one here. We must take the limit of this as delta t approaches zero, so that the time interval is very small or it becomes very little. And then since we are taking the limit now, this becomes our instantaneous acceleration. But you might notice that this formula here is something familiar. I think you have taken this up during your pre-calculus class. This is basically the formula for the derivative. For this case, the derivative of your velocity. Since this is your velocity and we're taking its limit as delta t approaches zero, this means that we can now therefore define this whole thing as just the first derivative of v with respect to time. And that's our instant acceleration. Instantaneous acceleration is what I meant. Okay, so from page 12, furthermore, we know that v is the first derivative of position x, or it's given by this relationship. V is the first derivative of x with respect to time, right? That's what this equation is telling us, this one here. So we can plug this in, this value of v here, to this value of our instantaneous acceleration here, to this v here in our instantaneous acceleration formula. Thus, our instantaneous acceleration will now look like this. So first, take note that your instantaneous acceleration is dv over dt, or which is this one from right here. But then since we know that v is dx over dt right here, we can substitute our dx dt here to get this term right here. To get this term. So dv dt, we substitute dx dt for v, we get d dt of dx dt, or the derivative with respect to time of dx dt. Now this will simply look like this one, or what do we mean by this one is that this is the second derivative of x with respect to time. Thus, your instantaneous acceleration is actually just the second derivative of position x. Okay, so this could be, let me erase some things. So this could be one of the ways you describe your instantaneous acceleration, or this could be the other way. So any of these two will follow or is the same, are basically the same. Okay, I hope this is clear. Just a reminder, the instantaneous acceleration is the first derivative of velocity with respect to time, or the instantaneous acceleration is the second derivative of your acceleration with respect to time. Okay, all right, take a look at an example. Okay, this is the example. Let's say you are given you suppose the x velocity of the car in the figure above at any time t is given by the equation. So this is an equation, this equation of v right here, the given, tells us of the velocity of our car. How can it tell us of the velocity? If we look at it here, we see that there is only one variable. M per s is a unit, m per s cubed is a unit. There's only one variable, which is t squared. So what we do is to use this equation to get the velocity of your car at any time. How do we do that? We would just need to substitute t to our expression right here. So if we want to know at a certain time instance, let's say at 2 seconds, what is the velocity of the car, we substitute t here with 2 to solve for our velocity. So basically that's an intro to our letter A. Let's first work on letter A. So we'd like to get the change of the velocity in the interval t1, 1.0 seconds, to t2, 3.0 seconds. But first, we need to get the velocities at each time instant given. So what do I mean by that? Since we are given this equation, we're given this relationship, and we know that we can use this equation to solve for v if we want to know what v is. So since A is asking us for the change in velocity of the car, all we have to do is to solve for the velocity at, let me get the highlighter again. All we have to do is to get the velocity at this time, which is t1, 1 second, or and at this time, 3 seconds, or t2. So all we have to do is to substitute those values to our equation. So now, let's first do t1. Let's first do t1. This is the expression describing your v, and since we are looking for the first velocity, we denote it as v1. Now we substitute time to be t1, right? So v1 is this expression, and then we substitute t for t1. What is t1? T1 is 1 second, so we just substitute it here. Okay, so that's how it looks like. Now we just simplify and solve. That gives us v1 equal to 60.5 meters per second. You can also do it on your calculators to check. Now we already have v1. Let's say we also want to solve for v2, which is our velocity at the second time instance, the one here, which is 3 seconds. So we substitute t2. So we are getting now v2. So your time now is going to be written as t2, and then we substitute for that. This should be t2 equals 2.0 seconds. I'm sorry I missed that. 3.0 is what I meant. So t2 now becomes 3.0 seconds here, and then we just have to simplify to get our answer, which is 64.5 meters per second. Now we already have a value for v1, we have a value for v2. Remember, for item A, we are looking for the change in the velocity at the time interval given to us. So all we have to do is to subtract v2 and v1 with each other. So to get the change in velocity, which is delta v, we subtract v2 and v1. We know v2, we know v1, we can now therefore just solve for delta v. So we substitute those values. So v1, which is 60.5 meters per second, and v2 as 64.5 meters per second respectively here. And then we solve. Thus, our change in velocity is 4.0 meters per second. Okay, I hope that's clear. That's for item A. It's looking for the change in velocity. For item B, we are asked of the average acceleration of our car. How do we get the average acceleration? We know that from page 9, or given by this formula right here. A is equal to delta V over delta T. And then we know that delta V is V2 minus V1, but we have already solved for it in the previous item A. So we already have delta V. We are looking for A. And do we know T2 minus T1? Do we know this? Yep, we know it. We definitely know it. We know T2 and T1 because it's the same time interval that we used in letter A. So we just substitute delta V to be 4.0 meters per second. That's from item A or from this one. We know T1 is the first time instance is 1 second and the second time instance is 3.0 seconds. We substitute these equations to here. Let me erase. We substitute all these here. T1 here, T2 there. All right, I hope you understand those arrows. So we just have to substitute and then solve. Thus, our average acceleration is now 2.0 meters per second squared. That's our answer for letter B. Okay, I hope that's clear. Now we work on letter C. We would like to derive an expression for the instantaneous acceleration. At the beginning of this video, we described how the instantaneous acceleration is defined, right? We define it to be the first derivative of the velocity with respect to time, or the second derivative of position with respect to time. How are we going to do that? Since we are given this expression, we are given this in our problem, and we see that this is an expression for v right here. We see that it's definitely v. We go back to that definition of our instantaneous acceleration, that it should be the first derivative of your velocity. Now, we already have an expression for our velocity here. To get the instantaneous acceleration, we just need to get its first derivative. So, how is it gonna look like now? It's gonna look like this. So, we take the derivative of v, which is dv dt. And then we look at the first term first. How do we take the derivative of a constant? This is basically constant, right? It's just 0. The derivative of a constant is just 0. And then for the second term, we bring down the exponent. So 2 now becomes a coefficient. 2 times copy whatever is left, 0.50 meters per second cubed times t with its exponent deducted by 1. So 2 now just becomes 1. This is now your dv dt. I hope you still remember how to take derivatives from your calculus classes. And therefore, our dv dt finally will look like this. This is our dv dt, or our first derivative of our velocity with respect to time. Now, Thus, this is going to be our instantaneous acceleration since we know, since from this definition, this is the definition of your instantaneous acceleration, right? And then, as we can see, this is our dv/dt. So we can therefore write our instantaneous acceleration to be this one, 1.0 meters per second cubed times t, time. Now, let me erase. Now, let's say we want to get the instantaneous acceleration at a given time. So at any point in time, 100 seconds in or like 2 seconds after it moved, all we have to do is to substitute t to our expression for the instantaneous acceleration here. So let's say we'd like to get its instantaneous acceleration at t1. Remember, t1 was at 1.0 second, that instance of time. To get the instantaneous acceleration, we substitute t1 to this expression right here. So instantaneous acceleration at time t1 is equal to 1.0 meters per second cubed times t1. We substitute t1 here as 1.0 second, and then solve, we get this one. The instantaneous acceleration at time t1 is 1.0 meters per second cubed. Okay, I hope that's clear. So that's the instantaneous acceleration at this certain time instant, 1 second. But let's say we also want to know the instantaneous acceleration at t2, or after 3 seconds of motion. Again, we only have to substitute this to our equation for the instantaneous acceleration. The a inst at time t2 is equal to 1.0 meters per second cubed times t2. And for t2 is 3 seconds. We substitute it right here. We get instantaneous acceleration to be 3.0 meters per second cubed. Okay, as I hope that's clear. As of this moment, you may now work on the digging deep activity right here and the your turn activity as well. You may pause the video here to check on the items, or you may reference your class notebook or your PDF. That's it for this part of the module. I hope you understood, and if you're still confused, you may reach out to me to ask your questions. Thank you.